Fleetminder because it integrates with anything that supports integration. The workflow automation here assists in configuration, provisioning, and inspection of the services. So what are those services? The Fleetminder server architecture is composed of several components, as I said. There is for the recordings of telemetry and basically any value that is sent by a fleet device, Victoria Metrics is used as a database. Then Loki is used for text files and for log files. These two components, Victoria Metrics and Loki, connect to the Grafana dashboard. And I believe we will show that later on. I'm also looking at Colin. The update server is the Heartbeat server. As I mentioned before, we do have some, well, it comes with quite a few challenges. And then to the right, we have Guacamole, which is a remote desktop server that connects to the SSH tunnel that can be created and opened on demand when that's necessary, such that you can log into a device remotely. And on top of that is the Nginx server, which connects to the Grafana dashboard and connects to Guacamole. So I'm going to switch back to the, bless you. I'm going to switch back to the terminal console. So if I explore these demo workflows again, then we see that a lot of them start with device, and some of them also start with server. So if I go for server, there is server start. The workflow engine supports integrated hello pages. So here, the server start command supports the R argument or any other string to reset the file system. It's obviously not what I'm going to do, because then it would need to rebuild, starting the server would require to rebuild the entire file system, which takes something like 5 minutes. We are just going to start the server as is. I can show the commands for those interested. Again, from this time, the workflow connects to tmux server and then starts the VM start script with a few options. So we're going to do this. Then we're going to switch to the QEMU window. And we see here that the server has been started. Linux starts. The init scripts, they run. And we see that a whole bunch of containers has been started. So these containers are obviously the containers that implement Loki, that implement Grafana, that implement Heartbeat, and so on. So switching back to the console window. One thing that I can do now, considering that we have a fleet device running, it's still running, and that we have a server running, we can register that fleet device at the server. I use batch completion again. I just have fleet device number 1 running, so that's the only one that I can register, obviously. During the registration process, the workflow first connects to Heartbeat to configure it appropriately. It then connects to the fleet device. The fleet device generates a few keys. These keys are then sent to the server, and then a few services on the fleet device are restarted, namely the Heartbeat update client and the FluentBit services. They are both restarted because they need to use the keys that were just generated on that fleet device to send data to the server. If I then, all right, so maybe it's interesting here to show the interactions again. because in this case we have used two roles within one workflow. So one we've used two roles. One role was used to configure the Heartbeat server. That was done from local user at localhost, and then from the device itself, the device registration script was started. So what is, if we want to inspect whether the registration was successful, we use other workflows. And what I'm showing here is that we can use these workflows to conveniently inspect all kinds of things that have happened or that are happening within our simulation. So in this case, I inspect the server device registration log, and I see that the Fleet device successfully connected to the server, that it issued a few commands. So we implemented a specific protocol for the Fleet device and the server to communicate, and you see the commands of that protocol, such as get SSH host keys, get remote access public key, which is used for Guacamole, registration for Heartbeat, and so on. And if I check what this then means from the with regard to the keys that are available on the server, then we see that we find the key of Fleet device 103 in the appropriate file of the server, meaning that the registration was successful. So these are the commands run on the server to figure out which devices have been registered. This configures automatically depending on the devices that are known by the demo target of the workflow engine. So what has basically happened so far is that I instantiated one device, I instantiated the server, I connected them, and at this very moment, the Fleetminder server collects recordings done on the device. But because of the way I exactly instantiated the simulation, it's a bit laborious to show this through the Grafana display dashboard. So Colin is going to take over the screen, and he will show the Grafana dashboard when we run a demo with, I believe, 5 devices.
Okay, so I will put the right window with the Grafana dashboard on the presentation. And I will let Hugo
Okay, yeah, sure.
present all the cool stuff about the dashboard.
Thank you, Colin. So Grafana is a software component that's highly configurable, and it provides docking elements that can display several different types of data. So we configured Grafana with several dashboards. This dashboard, which is called Node Exporter, shows technical data of one single device. So here at the top, I can select the device. So for instance, it's currently device number 1. Maybe I should also say the demo that is running now has 5 devices. So it's not the demo that I showed previously through the console window. This demo has 5 devices. It's the full-fledged regular demo, and these devices run the services that I mentioned before, so Loki and FluentBit, and connect to the server. But these devices also run one application, and I will get back to that in a moment. At this moment, I'm displaying the technical data of device number 3. As I said, I can change to a different device, or in this case, device number 5. We implemented a dashboard in Grafana that compares the different devices. Again, all technical data. So here at the top, you have CPU load, and the CPU load of the different devices are shown in sorted order. And we, as I said before, we also implemented a application on those devices. And this application, in this case, is kind of an invented application, but in this case, it sends data about geolocation, such that the Grafana dashboard knows to locate the devices on a world map, and the application sends battery information and a kind of arbitrary battery percentage. So this is only to show that the components that we selected for this demo have a professional grade, are actually used a lot in the real world. And yeah, that's basically what I want to say about that. Okay, so I believe Colin will now continue with a console demo. Yeah.
So I will not take over and present a console demo. Let me set up a few things first. Okay. I'm just finding the right window. All right. You should now all see my terminal. Sorry about that. And do you still hear me? So okay. You should all see my terminal now.
Yep.
And not other stuff. Good.
Yep.
So sorry, a bit nervous. So we recorded the demo using a tool called Askinema to avoid the demo effect, of course, but also to speed up some of the steps that might take a long time, and no one wants to wait for 5 minutes for all the devices to be brought up. So I will start it. Maybe zoom a bit.
Yeah.
So this is all a pre-recorded session. So you can see that this is done from the point of view of a fleet operator that wants to try out an update to the virtual fleet. So what we are going to do is, we already started the TMUX sessions that Hugo talked about before. And the overall idea of this demo is to start up the devices, the update server. That's more of a high level of the fleet point of view. We'll build a new update package. This uses low-level commands and high-level fleet management skills. And we will push it to the devices. And we will wait until they update. If they update, they do. And then we will try to tamper with one device, one artificial device, to see whether it will make something go wrong with the updates. So next command is I am going to find out which commands start the server, display the help, and start the server. So we can see that I use quite heavily the auto completion, and the help is always welcome. And this auto completion is why one of the reasons you will see that sometimes I make mistake when I type, because I rely on it too much, because it's a bit too useful. And now the server is started. So what happens now is that I start the devices. You won't see it because I'm busy talking. Again, it's pre-recorded, but now usually you wait for all the devices to be on. And then the next step is to see the rogue status so that you can see on which partition they booted in the AD boot scheme. So they all booted on the A partition, which is rootfs.0. So now we can just register the devices to all the fleet services, but mainly the fleet update service. It takes a bit of time, but it's done now. So the next step is to actually generate a package update with the potentially new version of software or patches, etc., and to push it to the devices. So we have made a workflow to generate a rogue bundle for the updates easily. So that's the one we are going to use. Sorry, I skipped a step. So there was already update bundle ready to be deployed. So that's what we just did. So the command you can see up above, you could see up above, this one is the one that pushed the update to the fleet. Usually it takes a bit of time with a simulated device that all the devices realize that there is an update to be applied, and to download it, to write it to the other partition and to boot it. But thanks to the magic of recording, this is instantaneous for you. Usually it takes something like 1 or 2 minutes for 5 devices. So you can see now that they are all on the rootfs.1 partition, which is the updated partition. And if I was to push another update, it would go back on the rootfs.0. For those interested, it's the AD boot scheme to avoid devices being built by an update. So this command, just up above, this one is the one that I talked about earlier that generates a new update package for the devices. So we generate it from the device development environment. And then we can start pushing a second update. And this can seem trivial at first, but actually making sure that the update mechanism preserves all the necessary configuration, like the network configuration, the update layer configuration, and other stuff, it's not that difficult, but it's something that can easily go wrong and cause a lot of problem. So one use case for these commands is to test whether this update deployment scheme actually works, which is very easy to do with a simulated fleet, much easier than using actual devices. And now we can see that the update has been pushed to the devices because it's now again on the boot partition A, which is the rootfs.0. So what happens now if we stress test the device? Let's say we make the CPU a bit busy by running stressng or something like that while it is updated. So here we created another update package to test that out. And what we are going to do now is to stress test one of the devices. I picked the device 5. I push the update. And now I stress test the device 5 using this workflow. We can see that it is indeed doing some stuff. This command is blocking, which for demo purposes is a bit impractical, so I have to control C it to interrupt it. And now I will watch out, I will watch how the update status of the devices changes with the time. So what I'm expecting is that the device with the stress test running on it will be updated later. So I will periodically run the device rogue status update, rogue status command to see the update status of the devices. When it fails, it's normal. It's because the device is still booting, so it cannot be accessed by SSH. So there we have 4 devices that have been updated, and the device number 5 is still doing something. Again, device number 5 is busy. And now it has booted. So we can, from a higher level point of view, we can test whether some particular condition regarding specific devices can affect the way they are updated. Here, there is no major problem because of that, but there is a lot more scenario where this could be quite a problem. Think about a Tesla stuck in an underground parking. What will happen? And I think that's the end of it. Yeah. Now I'll just stop the demo, and that's it.
I should take over screen?
Yeah.
Okay. It says still screen sharing. So can you guys see my screen? Can you guys see the presentation again? Okay, thank you, Rafael. So the demo that Colin just gave was about workflows and their configuration. So the highest level, it's quite obvious that we're only just scratching the surface over there. As I said, it's kind of an unexplored or not so well understood market. This basically ends our presentation. So we still have a lot of plans for future work. We're looking for a replacement for Hopit. We look at for a different device management system or implement one, or device update system. That's actually a mistake in the slide. We would also like to look at Mendelglot.io and similar systems. We've done an analysis for implementation of secure boot. We would like to validate the AB update implementation for physical devices. We have done some integration with a CI/CD, with GitLab pipelines, but that is only halfway of what it should do. And we would like to explore many more fault injection scenarios. Colin has showed one, but there's obviously a lot more to do over there. We're also looking at libraries that support this. One of these libraries, open source software library, is the GDB QEMU fault injection library, which I believe is indeed a very interesting suggestion that came from Colin this morning. I thought let's add it to the presentation. And then we also would have to do some more work for multi-account setup for Grafana. There are some workflows and scenarios there that we already implemented. I did not show those, but it's because they're basically just kind of touching the basics. And then with regard to research funding and looking for partners, we have done an investigation into secure network configurations and gateways, for which Fleetminder may be an interesting testbed. We should look at scale-up scenarios, and that includes then make the deployment of the 7,500 simulated devices that we already did, make that reproducible using workflows. There are interesting libraries for honeypot and decoy scenarios, and that may also introduce interesting commercial opportunities, I believe. And then one other thing, I believe a big one and a very interesting one is multi-tenancy and multi-partner data systems that for which Fleetminder could be a very interesting testbed again. This is the last slide of the presentation. I would like to thank all of the people who have contributed to this work, and I thought it was really necessary to add them a second time to this presentation. So thank you all to the audience. Are there any questions? Did we answer all the questions?
I think there is one from Jean-Christophe in the chat, unless it has already been answered, but I don't think so.
Why using an SSH tunnel in comparison to a lightweight VPN like WireGuard? Is this for the forward tunnel or the the tunnel that is instantiated on demand? That would be a first question. But then I believe the real I was not on the Fleetminder team when this decision was made, but I believe that the SSH tunnel was chosen because of its simplicity. As I've said a few times, Fleetminder is a modular system, and in principle we can change to any other software component that interested parties would like us to implement. Agnout is on the call, I believe, so if Agnout has a further answer as to why the SSH tunnel was chosen, that would be welcome, because I don't know the full answer.
The main reason was that it was the simplest thing to implement. With WireGuard, you have to distribute keys and IP addresses and do some dynamic updates of, well, not during onboarding. You have to do IP address assignment. It just felt a little bit more complicated. But yeah, WireGuard could have been used as well.
Okay, thank you. Yeah, that's a good question. So I will read the question from Ridwan. While using the full-fledged device update management service such as Heartbeat or Mender, the simulated devices are only about installing images that could be statically served. That's obviously correct. Why would we use Heartbeat or Mender? Because, well, we do this because a lot of people out there are doing it, and we still want to serve the commercial market. That would be my motivation. But as I said before, Heartbeat is not doing, in my opinion, it's not doing its job properly. We have faced a lot of challenges, and I would like to replace it with something else. Mender.io, I believe, is a very interesting candidate. But just for simplicity, I believe we will first implement our own solution for the updates. Actually, I have implemented a solution based on Nginx something like 2 years ago. So I believe it's possible to recycle that solution. Is that an answer to your question, Tito?
Yeah, it's how to say it? Just in the scenario here, I'm just wondering if Mender or Hogbit wouldn't get into the way. So they have pretty much advanced features such as like progressive rollout, where you test the first end device, and if that succeeds, proceed to the next ones, etc. And also they have very advanced features which here could interfere with the test, but I'm not sure exactly how it's used in a production grade project in that context.
Yeah, so for a production grade context, you obviously want to support things like Mender.io or Hogbit. So again, I believe that's the main reason why we use Hogbit and why we're looking at this moment at Mender.io. So thank you for that question, Tito. Then we have a question from Raphael. Do we have an idea of the minimal specs required for embedded devices to be able to run all the components that are currently supported? If not, what's the lowest? And we tested. Thank you, Hugo. Thank you, Colin, for the interesting presentation. Thank you for that, Raphael. Do we have an idea of the minimal specs required for embedded devices to be able to run all the components that are currently supported? The memory that we use on the embedded devices, I believe, is just below 300 megabytes, so that's not a lot. It's not small, but it's not really large. Well, Olivier seems to disagree. He believes it's a lot of memory. We have implemented embedded devices that had 4 gigabytes of memory, and there are devices that have only a few kilobytes. So in principle, a system like Victoria Metrics can support a wide range of devices because of its very simple protocol. So in principle, we can integrate with very simple devices, with microcontrollers, definitely. And I believe even with more simple devices than that. Whether is it interesting commercially? Yes. Is it feasible? I believe so, but we don't have a proof of concept for it. So I do believe that's a very interesting question, Raphael. Thank you. Are there any other questions? We're actually 10 minutes over time. So I believe this is a good time to finish this presentation. And I would like to thank all the people in the audience for being there. And I would like to thank all the contributors again. And also special thanks to Colin for his willingness in participating in this presentation.
No problem, this was funny.
So thank you very much, guys. And see you again in a month from now.
Please come back to my